In example number 3, it says find the extreme values of the given function. What you'll notice about example number 3 is we don't have a restricted domain. So without a restricted domain, we have to determine the domain on our own. And we know that the domain of a square root is restricted to being positive values. And we know that something in our denominator cannot be 0. So the domain of our function is going to exist in a way such that 4 minus x squared has to be greater than 0. And usually we put greater than or equal to 0, but again, because it's in the denominator, we cannot have the equal to 0. And then this is a quadratic. It's a difference of squares. So you have 2 minus x, 2 plus x has to be greater than 0, which means that the roots of this quadratic are at 2 and negative 2, which means that our domain is either going to be within negative 2 to 2 or outside negative 2 to 2. And what you could do is check by plugging in a number greater than negative 2 or between 0 or negative 2 and 0 or greater than 2. So if you plug in 0, 2 minus 0 is 2, 2 plus 0 is 2, 2 times 2 is 4, 4 is in fact greater than 0. Therefore, my domain is x values between negative 2 and 2. If you tried to plug in a number less than negative 2 or greater than positive 2, like 3, 4 minus 3 squared would be 4 minus 9. Well, that would give you a negative, and we can't take a negative square root. Therefore, our domain does not live beyond that. So the domain of this function is negative 2 to 2. And what you'll need to notice is that the endpoints are open. So if there's an open endpoint, the extreme value theorem does not apply in the sense that we are not guaranteed an absolute max or an absolute min because this is an open interval. And the definition of the extreme value theorem is that it has to be a closed interval. And what that means is we can't check our endpoints. However, f of x can still have critical points. We're just not guaranteed absolutes. So let's find our derivative. And honestly, the easiest to find this derivative is probably to bring our square root up as a negative. So I'm going to bring the square root of 4 minus x squared up as a negative 1/2. So that when I go to find my derivative, it's negative 1/2 4 minus x squared. You subtract 1, so you get negative 3/2 times the derivative of the inside, which is negative 2x. And then what's really nice about this is the negatives become a positive, because a negative times a negative is a positive. 1/2 times 2 becomes 1. So our derivative simplifies to x over 4 minus x squared to the 3/2. So we know that critical points come from when f prime of x equals 0 or does not exist. Now that does not exist will be points at which the derivative does not exist. So f prime of x can equal 0 when x, or the numerator, equals 0. So our critical point is at x equals 0. The other critical points would be when f prime of x does not exist, which would be when the denominator is equal to 0. But in the case of this problem, when the denominator equals 0, it's outside our domain because the denominator will equal 0 at the endpoints, which are not in the domain. So we only have one critical point, and that is at x equals 0. So x equals 0 could be an absolute max, absolute min, or it could be a local max and a local min. And we are going to determine later which of those it is. For now, you find f of 0, and you get 1 over the square root of 4, which is 1/2. And we just label this as a local extrema, because we don't know if it's a max or a min. Okay, find the extreme values of the given function. So what we'll notice here is we have a piecewise function. In order to be able to determine if it has extreme values, we need to determine if it is continuous and differentiable at x equals 1. So I'm going to find f of 1 for both the top and bottom equation. So what I'll notice is that this equation is not continuous. So if it's not continuous, then EVT does not apply. So again, this is not continuous, so EVT does not apply. It's also not differentiable at x equals 1. So if you were to find your critical points, they would be for x values less than 1, but not equal to. And then derivative of x is 1. So again, what you would notice is that the derivatives don't match up, their slopes don't match. And if f prime of x were to equal 0, that only occurs for the top equation, and that occurs at x equals 0. So again, x equals 0 can be a local extrema because it is a critical point. And again, it's important that I keep saying it can be. We're not guaranteed that because EVT does not apply because f of x is not continuous. So if it asks you to use the extreme value theorem, then you have to say EVT does not apply. So there are therefore no guaranteed absolute max or mins. Okay, find the extreme values of the function y equals x cubed. So its domain is all reals. It is continuous. So its derivative is 3x squared. The derivative equals 0 when x equals 0. But once again, what am I lacking? I am lacking a closed interval. If I restricted the domain, let's say -1 to 4, now I could have a totally different outlook, which would tell me that I have a critical point at 0. So this is my critical point. and potential extrema. If it's a closed interval, now I need to check my endpoints back into the original. So I need to find y of -1, y of any critical points, and y of the endpoints. So if you are given something that does apply to EVT, so if I were told the domain was -1 to 4, then EVT does apply. And I need to check the CPs and endpoints. So the CPs and the EPs. So we have y of -1. So you get -1 cubed, which is -1. We have 0 cubed, which is 0. And we have y to the 4th. So you have 4 cubed, which is 64. And what we'll notice is the reason that CP was a potential extrema, and it is not, is even when you compare it on a closed interval now, my absolute max is at the starting point. Oh my God, my absolute min, rather, is at my starting point, and my absolute max is at my end point. 0, which was a potential extrema, isn't even a absolute max or absolute min on that domain. That's not to say it's not a local. We'd have to plug it in and compare to the left and to the right, which we're going to do next section. Okay, we've now learned exponentials and natural logs. So it says find the extreme values of the function y equals the natural log of x divided by 1 plus x squared. We know that natural logs can be written out. So the natural log of x minus the natural log of 1 plus x squared is equivalent to that initial conditions. And then we're also told that they're absolute values. So that's kind of like, and it's already an absolute value in a sense anyways, but that absolute value is important, especially for the x in the numerator, because we know we can't take the natural log of a negative number. And by turning that into an absolute value, it makes it that the domain is unrestricted, because now, no matter what answer you get, we're turning it to a positive. So originally, the domain of a natural log is such that x has to be positive. The absolute value in this composition kind of takes that domain restriction away. So our derivative becomes 1 over, and we're going to keep that absolute value of x, times the derivative of x, which is 1, minus 1 over 1 plus x squared, times 2, and we're going to add back in that absolute value of x. And what we'll notice is we have absolute value of x over absolute value of x, so those end up canceling. And we get 2 over 1 plus x squared. And I don't have to worry about an absolute value on the denominator because anything squared will be positive. So I don't have to be so concerned in this case. So my derivative looks like this. We set it equal to 0, and we get 2. Well, 0 never equals 2. We set the bottom equal to 0, and we get -1 equals x squared. We know that x squared can never be a negative, so our derivative has no critical points. Our derivative has no critical points, which means we have no potential extrema. So find the extreme values of this function. There are none guaranteed. So today was a nice little lesson, just kind of potential possibilities of functions that are a little different. You're going to continue your homework in the textbook in that section 4.1. I believe it's page 193. You're going to pick up yesterday, you did 1 to 4. Today, you're going to do 5 to 15. We already did 19 to 22, so we're going to pick up with 23 to 30, and then 45 to 49. Before I release you and have you working on that assignment, were there any questions on any of the homeworks from last night, or 2 nights ago, I guess, on Monday? Okay, and then if there are no homework questions, like I said, I'm going to spend today grading your quizzes. Hopefully I'll be able to give those back to you tomorrow. Make sure if it asks you to use EVT, that you make sure all of the rules for EVT apply. So extreme value theorem says it has to be continuous on a closed interval. And if it's continuous on a closed interval, then you are guaranteed an absolute max and an absolute min. But again, only if it's continuous on a closed interval. If it is continuous but not closed, then you could have local maxes and mins. If it's closed but not continuous, then you are not guaranteed anything. Critical points, by definition, are potential. So again, a critical point is a potential, not guaranteed, a potential extrema. So the critical points of the derivative are potential extrema. And they occur when f prime of x equals 0 or does not exist. All right, guys, have a wonderful day. Thank you.